Hello, in this video we're going to be looking at polynomial functions and some of their graphs. All right, so on the screen here I've got three functions here, and I'm going to tell you that they are all polynomials. Now let's have a look at another group of functions, and I'm going to tell you that these are not polynomials. So I'll just write that here. These are not polynomials. So see if you can see what's different about these to these. All right, I think you see it. It's about the powers of x. So here we have a power of 2, a power of 4, a power of 5. I hope you can see a power of 1. So the powers all seem to be positive there. But here we have a half. Here we have a negative. What's wrong with this? Oh, it's got a sign in it. That doesn't look algebraic at all. So it's got some trig in it. Okay, so it can't have trig in it. And square root, well, it's not that different. Let's just rewrite that to the, but it's a half. Okay, so hopefully by now you're getting an idea what makes a polynomial a polynomial. So a polynomial it's an expression in x that has positive integer powers. That's a quick way of thinking, or 0 actually, or 0 as the power. Because when we look at this guy, what is this guy? -5. It's actually x to the 0, so you can think of it that way. So if we say we can have any powers 0, 1, 2, 3, 4 and above, we're all good. No fractions, no negatives, no trig, please. Nothing else fancy. It's essentially this form. All right, let's learn a few keywords. And the few keywords we have are the degree of the polynomial. So the degree of the polynomial, I'm going to tell you this first one is called a second degree polynomial. This one's called a fifth degree polynomial. And this one's called a first degree polynomial. Can you see what I'm doing? I'm looking for the highest power. So if I wrote this one, y equals x to the 7th minus 3x to the 10th plus 5, we would say it's a degree 10 polynomial. So the degree of the polynomial is the highest power value. All right, let's just recap what the word coefficient means. Coefficient are these numbers in front of each term. So there's a coefficient of 1, there's a coefficient of 2, coefficient of 5. And finally, the idea of the constant term. The constant term is just when we have a whole number. That's called the constant term. Okay, let's just write that out so we can see it clearly. Our nice polys. All right. So why do we care? Why do we care about polys? Well, it turns out if we accept this restriction, we get nice, well-behaved functions. Nice, well-behaved functions that essentially give us nice shapes like this and this and this. And they don't have any broken pieces, so to speak. They're quite well-behaved group of functions. And we're going to learn about them as a whole category. So we've met the first three in the family of our polynomials. This is our linear function. So y equals, say for example, 3x plus 5, and it's got a power 1. We've met our quadratic functions, and these are polynomials in power 2. So this one might be something like this. And finally, the cubicies. We're just becoming more familiar with them. This one could be 2x x cubed minus 5x plus, well, it's going through 0, so we'll just leave it like that. Just a little note. Sometimes it's confusing. You see the word quad here, you might think 4. It actually relates to 2 because it comes from the word for a square, which has 2 by 2. Okay, so even though we say quad, we may think 4. It comes from a square, the squaring process, which does have 4 sides, admittedly, but it's a square. So this is a second degree poly, a first degree polynomial, and a third degree polynomial. All right, some new friends to add to our family. We've done first degree, second degree, and third degree, and it's definitely time for a fourth degree. And so this one is a fourth degree, which means it's someone in x to the 4 who's got some other terms. And this one is actually a positive one, so it's one that's going. I call this guy an uppy because he's heading up. Notice it's a bit like a parabola, but it's got more bumps in it. Here it's got quite a few little bumps. And in fact, it's not a coincidence that there could be 3 bumps in an x to the 4th. If you think about our parabola, we have 1 bump in x squared, and in our cubic, we can have 2 bumps in our cubic. So that's an x cubed, that's an x squared, and in our x to the 1, we have none. All right, so this is often called a W shape. When we flip it over, we'll get sometimes what's called an M shape. So this is what I call a down version, or a downy. This is what I call an up version. And so that's our quartic. Here's the quintic. So the quintic is x to the 5th. And you may notice my x to the 5th has got 1, 2, 3, 4 possible bumps. This is what I call an uppy quintic. So this is positive x squared, x to the 5th plus something. And this one is a downy one. It's negative x to the 5th, blah, blah. And it might look a bit familiar. It looks a bit like the cubic keys, but with more bumps. You may have actually noticed a pattern happening here, and we'll just draw a few. If we have x squared, so x squared is going to look like this. X to the 4th can look like this. Sometimes it will look quite parabola-ish, but a bit of a flatter bottom. X, so that's x squared, x to the 4th. That's also another version of x to the 4th. Some extra stuff. X to the 6th could have more bumps, but they all maintain that same shape. Whereas the odd degree polynomials, there's x to the 1. This is odd degrees. X cubed. X 5th. And x to the 7th. Okay, we could have them going down like that. Have quite a different shape. So you'll notice that with the positive ones, even degree polynomials, it's like they're starting and ending points where these parts always end up in the same place, whereas in the odd degree ones, they end up on either side of the x-axis. And I'm going to let you think about why that is. And the answer comes down to thinking carefully about why is the parabola in this shape, whereas x cubed is in this shape.